Welcome to the control and simulation session. Let me introduce Joe, who's going to talk about inferring smooth control. And he's presenting from work in TU Darmstadt.
Thanks.
Thank you.
Hi, folks. So thanks for the introduction. I'm Joe, and I'm a PhD student at TU Darmstadt, and I'm presenting some of my work on approximate inference methods for Monte Carlo control. So our primary motivation for this work is sample-based model predictive control, which has demonstrated really impressive results on complex, high-dimensional, non-convex tasks. But one issue with these methods is that if you look at the robots and if you look at the telemetry, despite the good performance, they have kind of weird solutions, which could be characterized by kind of rough actions and also kind of abusing the actuation limits. And so what we kind of looked at in this work is bringing in Gaussian processes as a distribution over action sequences and using the correlations between actions in time to kind of incorporate smoothness in the robot control during the optimization. And so to explain where these correlations kind of come in, I just want to give a brief overview of how sample-based control works. So what we're doing is we're doing open loop control over a finite time horizon, and usually we kind of specify some parametric action distribution. And in order to explore, we kind of sample from a joint distribution over action sequences. And here's a key detail, because in this joint distribution is all the correlations that kind of capture smoothness. And then one kind of key issue with a lot of implementations is that people make this independence assumption in time, which kind of gives you this IID random noise for exploration, and then results in these sort of rough trajectories that you have to use for optimization. And then in order to kind of improve, you need some kind of weight per action sample. And this can be some kind of soft weighting or some kind of hard weighting. And then in order to do the next kind of iteration, you then project these weighted samples back to a parametric distribution. And this is the other kind of key step, because in order to kind of preserve this smoothness, you need to capture all the correlations from your kind of iterates in this parametric distribution. And we kind of take the inference perspective because it gives you a kind of very elegant way of thinking about where these weights come from. And Takayuki kind of talked about it a lot earlier. Where in the kind of episodic setting, we're optimizing for the return. If you introduce a KL constraint between your posterior and your prior, then you get this closed form solution that's used across machine learning called a pseudo posterior or a Gibbs posterior. And this is like a Bayes posterior, but our likelihood is now kind of incorporating our optimization objective. And then optimization in the Monte Carlo setting, the weights kind of come from this important sampling procedure. And posterior policy iteration is this idea of using these pseudo posteriors for optimal control. And we had kind of two research questions in this paper. So the first is how to design priors for control and kind of how can we use Gaussian processes. And the second is how to kind of modulate this temperature alpha during optimization to kind of balance optimization and inference accuracy. And in the interest of time, I'm going to focus on the first question, but if you're interested in the second, come find my poster later. Okay, so why do you want to design action sequences for control? Well, I think kind of in this room, we're all roboticists, and we know that IID noise in robots is not really desirable for physical systems. Not only is it going to damage the robot, but probably the environment as well. But also, I think as humans, we're kind of biased towards smooth solutions that kind of move like we do. And also kind of looking in the literature, a lot of sort of implementation details for these sample-based methods need to incorporate some kind of notion of smoothness in order to work well on real systems. So for example, doing some kind of first order smoothing. And the kind of general reason for this is that you want to kind of sufficiently smooth your solution so it's good to run on a real system. But of course, with these first order methods, you don't want to introduce too much lag. But then also there's lots of work kind of showing that if you sample smooth trajectories as well, you can incorporate a lot of Monte Carlo efficiency by kind of searching a more informed solution space. And what we kind of argue in the paper is that non-parametric Gaussian processes are a very kind of principled and elegant way of thinking about these kind of models because they're inherently a kind of very rich representation of smooth stochastic processes. And so by choosing some kind of covariance function, so we use the kind of popular squared exponential kernel, we can define this joint distribution, and sampling from this joint gives us very smooth action sequences that we can then use for MPC or policy search, and then kind of also incorporates into the sort of approximate inference procedure that I introduced earlier. But then the kind of key issue with the kind of problems we're interested in is how can we scale these non-parametric GPs into high dimensional MPC tasks? Because ultimately we're optimizing this matrix A, which is over both the time horizon and the action dimension. And if we were to naively just flatten this matrix into a vector, this would give us a really large covariance matrix that in practice you don't want to use for computational reasons, but also numerical sensitivity reasons. And so what we kind of use in the paper is what's called a matrix normal distribution, which, as the name suggests, is a kind of twist on the normal distribution, but for matrices. And the key kind of detail is that it introduces two covariance matrices, K and sigma. And so the K is a covariance over the inputs, and then sigma is a kind of covariance over outputs. And they kind of arise from this kind of structured covariance of the flattened matrix, which is a modeling assumption that kind of gives you a lot of nice scaling properties. And it's useful for us for control because it means that this input covariance, we can now use our covariance function over time and kind of capture our smooth correlations. And then the output covariance over actions, we can just fix to something sensible based on the action limits. And so now for MPC, where our time horizons are usually quite short, we have quite a small covariance matrix that we can use a GP with quite happily. What's also interesting is that in model predictive control, we want to kind of project our solution into the future and kind of play around with kind of planning into the replanning. And using GPs gives you a very kind of elegant way of doing this because they're defined in continuous time. So using Bayes' rule, you can kind of project your solution using the prior forwards and backwards in time, but also at different time discretizations. And while the math is like a bit involved, because it's all kind of using multivariate normals, it ultimately boils down to some linear algebra operations that aren't too expensive to use. And so for the experiments, we kind of looked at these sort of high dimensional MuJoCo tasks for MPC. And not only could we kind of solve the tasks reasonably well, but also when we found this sort of side effect where even though the action regularization term kind of hasn't changed in the kind of RL setting, just the idea that the inductive bias of smoothness provided by the GP gives you much reduced amplitude of the actuators in the solution, and we kind of attribute this to the synergy between smoothness and energy efficiency that we've kind of seen in the literature. And then looking at a kind of broader kind of suite of tasks and doing a sort of frequency-based measure of smoothness, we found that sort of our solutions based on posterior policy iteration in blue and cyan not only kind of matched kind of current state of the art in terms of Monte Carlo MPC sort of efficiency, but if you look at the smoothness measure on the bottom, we could kind of achieve a factor of 2 greater smoothness by using the Gaussian process, which was kind of very evident in the kind of simulated results. Okay, now for some dirty laundry. So compared to the kind of IID assumption, Gaussian processes introduce like a lot of implementation complexity and maybe some numerical sensitivity, although I didn't see it too much in the end. GPs also kind of introduce a hyperparameter, so the length scale, which you typically just kind of have to tune offline. In the paper, I discussed trying to learn this length scale from expert demonstrations, but I was kind of surprised to find that it's very difficult to extract this smoothness from many expert demonstrations, especially those from sort of deep RL agents. And yeah, so thank you for listening. This is joint work with my supervisor, Jan. And you can find the code and the paper online and come find me in the poster session later.
Thank you, Chair. That is lovely. Do you have any questions? Yeah.
So you said you learned from expert demonstration. Did you also consider including some sort of non-expert demonstrations? Okay. So for high parameters, did you also consider including some non-expert demonstrations?
What do you mean by non-expert?
Like just other trajectories to get the smoothness.
Yeah, I mean, I think the key kind of issue I found was that quite often in either, so with DeepRL, it's because of this sort of random noise in the exploration, this tends to kind of infect the sort of solution of the policy. So it just tends to be inherently rough. So we don't see the kind of smoothness we maybe expect in optimality in these kind of optimized agents. I think with data kind of generated from kind of human demonstrations, I think it's maybe more of the sort of artifacts of measuring that kind of corrupt the readings that makes smoothness kind of difficult to extract from there.
Okay. And one other question is, did you try any other kernels except for squared exponential?
Yeah, so you can use Matern or periodic kernels. I mean, I tried to use periodic kernels for locomotion because I kind of thought that this would maybe be like a good inductive bias, but in practice, because locomotion also kind of includes a lot of non-periodic behavior to kind of get started, you really didn't see a meaningful like benefit, or it just didn't work at all.
That's great. Thank you very much. I have some questions of myself, but we're short on time, so I will ask you later.
Okay.
So our next speaker is Ian.
Yep.
He'll be talking about real-time mapping of physical scene properties, an autonomous robot experimenter. Let's see if we can get that up on the screen. Yeah.
Hello. Yeah, so my name's Ian. I'm a robotics research engineer at Dyson. And the work I'm presenting today was done in collaboration with Imperial College London, where Dyson funds a robotics lab as part of its sort of giving back to the community. So to perform complex tasks, an autonomous agent must build a rich internal representation of a scene. This should extend beyond geometry, color, and traditional semantics to include physical properties from which robotic affordances can be inferred. In this work, we present a real-world robot that learns about its environment through autonomous exploration and experimentation. With only a handful of targeted interactions, a task-driven internal representation of the scene based on a neural field model is built from scratch without any pre-training or external guidance. Our solution operates at the intersection of several research domains. And in the case of online scene understanding, we build on our previous work of IMAP and iLabel, bringing together real-time SLAM, semantic labeling elements to create an autonomous robotic system. It's worth emphasizing that our approach is generalizable and applicable to any task-driven experiments. However, for demonstration, we focus on 3 modes of interaction. The first is top-down poking, measuring the rigidity of objects, hard or soft. This is a discrete measurement based on the measured impulse force during object compression. And we assume that rigid objects are never placed on top of flexible ones. The second mode is spectroscopy, where a measurement of material type is obtained by placing a hyperspectral sensor in contact with the object's surface. Classification is achieved by passing reflectance amplitudes through a pre-trained SVM that's assumed to have seen all material classes beforehand. Again, this is a discrete measurement. And finally, the third mode is lateral pushing, assuming that objects are both rigid and free to move. A small lateral push is applied to the object and the minimal push force required for object motion measured. Unlike the previous 2 measurements, this is a continuous valued property. To incrementally build a neural field representation from scratch, the robot is equipped with an RGBD camera and hyperspectral sensor. Its pose is tracked using the forward kinematics of the arm. And as the robot moves around the scene, it captures various keyframes with corresponding poses and stores them in keyframe arrays. Simultaneously, in real time, a small MLP is trained to predict RGB, volume density, and physical property from input spatial coordinates. At any point in time, the network can be queried to produce a rendered image of any output. In this way, the MLP is incrementally trained by sampling ground truth points in captured keyframes and comparing them to rendered counterparts, feeding back the resulting loss. Measured physical properties are sparse, yet we observe them to densely propagate over coherent objects. This is thanks to the common backbone of shared weights in the network, from which all predictive heads originate. Hence, label propagation is guided by the densely supervised RGB and depth. The neural field model can facilitate autonomous exploration. At any point in time, the network can produce a pixel-wise labeling of physical properties. And from this, we can calculate the label entropy and use it as a spatial measurement of model uncertainty. High entropy equates to high uncertainty. And for efficient exploration, we want the robot to focus on regions of high uncertainty. However, we found interactions at object boundaries where entropy is always high to be undesirable, often leading to misclassifications or tipping objects over. And so to reduce their occurrence, we apply filters to the uncertainty map, Gaussian blurring and clipping above a threshold. This combination is referred to as the exploration metric, and it causes the robot to focus on regions of high uncertainty, yet ignore regions of maximal uncertainty, which are problematic. Kinematic feasibility for each mode of interaction is also considered. And for this purpose and that of collision-free motion planning, a collision mesh and a normal map are rendered from the network. As the robot explores, I'd like you just to focus on the bottom left, showing the entropy going from high to low, which is red to blue. And again, I want to stress that this fully autonomous behavior is achieved using a single MLP to drive the automatic query generation, the kinematic feasibility checking, the collision avoidance, and the interaction planning and execution. Material and rigidity prediction may be viewed as segmentation problems, and in both cases, the semantic head of the MLP predicts a discrete category. Whereas with lateral pushing, for the first time, we demonstrate the prediction of a continuous valued property in the semantic head of the MLP. Coming from a physics background, I find this particularly interesting because with only a small number of interactions, in this case 3, we can get in essence a map of a very complex mass distribution, which is obviously very useful in manipulation. In this mode, interactions between the robot and the scene introduce object displacements, violating the static scene assumption that allows optimization from an expanding set of keyframes. And so to overcome this, we clear the keyframe history and corresponding labels after each interaction. Experimentation suggests the neural field possesses a form of temporal memory, whereby network weights adapt and maintain consistency with the dynamic scene, provided the scene changes are comparatively small. The main limitations of our system relate to its self-awareness of errors. Each mode of measurement has an associated accuracy, and we observe that although the model recovers after an erroneous measurement, it requires significantly more interactions to do so. You can see many more blue measurements are made in order to correct or rectify the incorrect green measurement. Furthermore, there's always the possibility of catastrophic disturbance, preventing the model from propagating labels effectively. Here you can see the reconstruction becomes blurry after the object falls over. Okay, so in summary, we've demonstrated a fully automatic robotic, a real-world robotic platform that can build meaningful representations of its environment. In the future, we hope to extend the system with new task-driven experiments. This might include probing the scene with various tools or grippers to directly build affordance maps, or to measure extended physical properties with alternate sensors. Thank you for listening, and I'll also be at the poster session, so please come speak to me if you've got anything you want to know about the work. Thank you.
Thank you, Ian. That was very cool. Any questions from the audience? I have a question. What do you think is so imagining this line of research further on, what is the most complex instance of a problem that you can imagine solving with this?
I don't know. I think one of the things I wanted to explore next really was actually bringing modes in at the same time. Because as you introduce each mode, say you're measuring an object is hard or soft, but maybe you're also measuring, I don't know, whether it's metallic or it's got lots of friction. All these different modes can help you build up a better scene representation because they all help each other with segmentation and various other properties you might be interested in. So I think you can add a lot more complexity by having more sensors, and that's only going to improve your scene understanding.
Mm-hmm. Thanks.
My question is a follow-up. It would seem that including tactile sensing is a very obvious sort of way of improving.
Yeah, I think
Let me just repeat the question.
Yeah.
Roberto is asking about tactile sensing.
Yeah, that's a very nice question. I think bringing together RGB depth with tactile. Obviously, tactile sensing is a very sparse measurement, or can be, and you can combine that. The nice thing about this neural field representation is that you can combine everything in this implicit representation that gives you a full description of your environment. You can train it from scratch, and you can essentially feed in whatever sensor data you want. And yes, tactile sensing is a very good one because it's sparse, and it's only going to improve your RGB, your depth prediction, your overall mapping and scene understanding. So yeah.
Okay. I mean, we're kind of out of time. All right.
Okay.
Thank you so much, Ian. All right. I think we're supposed to be hearing from, where is this? I'll tell you the title of the talk. Rethinking optimization with differentiable simulation from a global perspective. I'm not sure who's presenting. They're online. Do I need to do something? Oh. What do I do? There she is. Hi, Rika. I
Hello,
can see
can you
you.
hear me?
Yeah, you're good. You're good to go. Go for it.
Wonderful. And can you see the slides as well? Yes?
Yes.
All right, perfect. So in this work, we call for rethinking optimization with differentiable simulation from a global perspective. And we consider a variety of optimization problems, including policy optimization tasks with highly deformable objects and liquids, as well as real-to-sim tasks where we optimize the behavior of simulated objects to match reality. And our contributions are differentiable simulation environments with various objects and interactions, analysis of optimization landscapes and gradients, and the global search method for optimization on rugged loss landscapes. We construct several new scenarios with rigid objects, a particle-based simulation with fluid, and mesh-based simulations with highly deformable objects. We also incorporate a number of particle-based environments from the plasticine lab that simulate plastic deformation. We challenge the assumption that differentiable simulators provide easy optimization landscapes in sufficiently interesting scenarios. Our visualizations of lost landscapes uncover numerous local optima, as you can see here in examples from our fluids scenario. And here's an example of a landscape with flat plateaus showing the need for extending gradient-based methods to have global search. We propose an approach that uses Bayesian optimization to explore the loss landscapes globally, and it models uncertainty over the loss here using Gaussian process and reduces the uncertainty by exploring unseen regions. At each global iteration, Bayesian optimization proposes the next vector of simulation or control parameters to try. We treat this as a starting point for what we call semi-local leaps. We first sample a population of K candidates. Then from the best candidate, we compute the starting point for the gradient descent. And then the gradient descent that we call the leap part of the method proceeds, since on the smooth loss landscapes, it can make fast progress towards an optimum. When the gradient descent reaches the local optimum, we again sample K candidates in a gradient-free way. And from the Gaussian distribution, whose mean and covariance are computed using covariance matrix adaptation equations. So then we again compute the descent start and then proceed with the descent and so on. In the outer loop, we update the Gaussian process posterior for Bayesian optimization, and then Bayesian optimization selects the next point to try globally. And it ensures to return to low loss regions to further improve within the promising areas of the search space. In the experiments, we first show that gradient-based methods can offer significant gains compared to gradient-free approaches, such as CMAS. And here's an example with a 3-link pendulum that has to reach the blue dot. And we also study extended versions of the task. Here, the cart pull starts further away from the goal and the action ranges are increased. So the cart pull can reach the goal faster, but it is also harder to find a stable, successful trajectory. In the rope scenario, BO leap succeeds to wrap the rope fully around the pole, while CMAS leaves a gap. And here's an extended version of the task where the white anchors start further away from the ends of the rope. And this is an assembly scenario where the goal is to hold the deformable sphere between the two anchors and lift it up and place on top of the cube. And BO leap lifts up the deformable sphere while CMAS squishes it too much and struggles to lift it up. We also here experimented with an extended version where we place the anchors further away from the sphere and sometimes get like interesting behaviors here that are somewhat unexpected. Our setup for the real to sim experiments consists of a Kinova Gen 3 robot arm, 2 real sense depth cameras, and a deformable object. And here the objective is to optimize the deformable cloth in simulation to match reality. The loss is computed based on the distances to the 4 corners of the simulated cloth that we also annotated in the real point cloud. And here's an extended version where we've increased the number of parameters to optimize. Gradient-based methods can succeed in matching the overall motion for this highly deformable cloth. And next we study the motion of cloth that behaves more like a paper towel when lifted, so it's stiffer. And here, some dimensions of the lost landscapes are relatively smooth, but others can be quite rough in some scenarios. And nonetheless, gradient-based methods can still perform well and find the parameters for the deformable that make it roughly match the paper motion. And here's also the visualization of the performance where we have the extended version when we double the number of parameters to optimize. Next, we study the fluid scenario where the goal is to lift up the sugar cube from the liquid. And we also have an extended version where we lift up 2 sugar cubes. And here our method outperforms other gradient-based methods and gradient-free methods in this task. And then the next set of experiments would deploy the policies that we optimized, but now on hardware. And so BO leap here lifts up both cubes in 7 out of 10 runs. BO is the closest competitor, BO with descents, that succeeds in 3 out of 10 runs. CMAS could lift 1 of 2 cubes in several runs, but it failed to lift up both cubes on any runs. And it often also failed to lift even a single cube. In these experiments, as you can see, we use a smaller container for liquid to avoid spills, and we use foam instead of sugar for the cube, but the motion of the cube in liquid is similar to simulation. So the setups retains the challenges of keeping both cubes within the ladle, and here we're showing an example of a failure of both of the tasks. Both of the algorithms. So we were asked to provide a kind of the dirty laundry list. And here, our first note here is that we like the cinematic rendering, but it is slow. So internally, we're using a faster renderer that gives us an idea of what is happening with simulation. But of course, it takes much less time to render. From the algorithmic side, the biggest headache is that matrix decomposition for CMAS, BO, and so therefore also for BO leap cause non-determinism. And this can sometimes compound to basically have instabilities that results in plots that look different between runs. The side effect of this is, for example, here in paperless scenario, where we run 10 seeds, and we kind of see some ordering of the performance of the different algorithms. But when we proceed to run more seeds, the ordering kind of like changes up a bit. So it's a bit challenging to kind of run a lot of seeds. And for these slower environments, we can only afford to run 10 seeds if we have many environments to experiment with and many algorithms to compare. So rather than basing our conclusions on how algorithms perform in a particular environment, we now tend to look at the bigger picture of how things perform overall across a wide range of environments. All right, so now the dirty laundry list is done, and there's still something to note, not really about our work in particular, but generally about differentiable simulators. The biggest challenges here arise due to difficulties in differentiating through rigid contexts. And with the spinball scenario, we studied this issue by varying the number of contexts, by changing the number of colliders in this game. And here's another example. This time, the context between the rigid and highly deformable object yield a rough landscape and low quality gradients. And so this is despite the fact that dynamics of the environment appear well behaved. So overall, to summarize, the messages that we would like to communicate with our work are as follows. The first takeaway is that well-behaved dynamics does not necessarily yield smooth loss landscapes and useful gradients. The second takeaway is that particle-based simulations often yield high-quality gradients, so they could be useful despite the increase in compute and memory requirements for them. And lastly, global search with semi-local leaps can be a valuable tool to tackle rough optimization landscapes. It is beneficial for optimizing more advanced differentiable simulation scenarios that have various kinds of interactions and deformables. Thank you, and I can take questions.
Thank you, Rika. And Roberto, again. You say, I'll repeat.
Thank you, Rika. Very nice talk. I have a question specifically about the choice of Gaussian processes as model for Bayesian optimization in this case. So a lot of the landscape that you are showing seems to be very sort of difficult to solve with stationary kernels, and modeling this sort of discontinuities or sort of very jagged landscape would essentially be very difficult, especially if you have a single length scale, right? So my question sort of goes in the direction of asking whether, first of all, whether Gaussian process is the right choice of model here, but also in sort of suggesting that maybe the right comparison here would be to have something like a multi-scale Gaussian process, because it would seem that using gradient descent in conjunction with, in this particular case, GPs, you probably are going to get fairly bad models out of the GP. And what gradient descent is really doing is to basically compensate the fact that you cannot really model this landscape. So maybe having some sort of multi-scale, model where you can better model the landscape in the first place would actually behave, equally well, or certainly better than a standard sort of vanilla BO. Yeah, sorry for the long question.
That's perfect. This is a wonderful question / comment. And in fact, as you probably might have guessed, I indeed tried a whole number of recent works in non-stationary kernels. One of them I compared fairly thoroughly to this. The biggest problem with them is that we are handling maybe about 1,000 kind of points here, and some of them go up to 200, 400 dimensions. And so some of these like cutting edge works, they generate like really nice visualizations at the beginning. And the problem is that they kind of like become prohibitively expensive for slightly more interesting environments. So, for example, I could get like really nice visualizations for non-stationary kernels for like, let's say, smaller, like lower dimensional versions of CoRL. But as I started to scale up, that became kind of like really, really prohibitive in terms of cost. So that was one consideration. And of course, yes, you're exactly right that a non-stationarity here in the kernel will be exactly what we would want to address. I originally also for this project really wanted to try to learn the kernel, as I usually do, from simulation. And so I think this would be my next step. Except here is a little bit interesting of kind of like how to do this, because usually what I do is I resolve non-stationarity by training the kernel in simulation, then deploying Bayesian optimization on the real robot. And here, the whole point of the work was like, oh, well, can we get going with the optimization right away and kind of benefit from the speed? Like we don't need this black box optimization, like in preliminary stage of collecting the data. And so I couldn't kind of resolve this trade-off, how to both say, okay, we can start optimizing right away, but also be able to handle non-stationarity in this like training kernel from simulation way. So this I think is like a very interesting future work, and I will be looking still for the methods that pretty much just like general methods with non-stationary kernels without training from simulation, just non-stationarity in the kernel that somehow can be adaptively kind of trained. But they are slow. So basically the reason why I didn't go in that direction is because we really wanted to kind of like keep it open for being able to handle kind of higher dimensional problems. And that was kind of a little bit prohibitive in terms of cost.
All right, thank you very much. I'm sure there are more hands up, but we are on a slightly tight schedule. No, sorry. I don't know. How do I know if these people are, we have a paper from Gabe and Phuket. Are they presenting live or also online? All right, go and hook yourself up. Thank you so much, Rika. It was a really nice presentation.
Okay, thank you. Bye.
The next paper is called Walk These Ways. Gate conditioned policies yield diversified quadrupedal agility. Yeah, we can see your screen.
Oh, okay. All right. Hi, I'm Gabe. Let me begin by showing you some videos of our locomotion controller. It can hack through thick vegetation, climb over large rocks and gravel, duck underneath obstacles, manipulate payloads, and even compose behaviors together to dance, like at the last RSS banquet. You might be thinking that to obtain these behaviors, we created simulation environments for each of these different scenarios. However, let me tell you that all of these skills were learned in the same simple flat ground environment, shown here. Your next question might be, why not simply model all of these scenarios? Why train the robot in isolation on flat ground? Consider the typical paradigm for sim-to-real learning. First, the designer models some environments they anticipate the robot will see in the real world. In locomotion, these might be different types of terrains. Then we deploy the train policy and it experiences some new environments. The designer may realize that the robot is not behaving well in these new environments. They will go back and add these environments into training. But there will always be new environments that were not encountered yet. The designer cannot practically model all of these. And worse, some terrains we cannot model in simulation today, even if we have identified them as important. So what should the designer do? To study this problem, we'll consider an extreme instantiation. We will only train on flat ground and consider generalizing to unseen environments. To gain intuition, let's start from a simpler problem of binary classification. Here is one decision rule that achieves zero training loss. Here's another, and here's another. So there are multiple ways to achieve zero training loss. Depending on our regularization, we'll end up choosing one of them. Suppose we choose hypothesis H1. Now we encounter some test data, the hypothesis generalizes. But under a different set of test data, H1, which was successful in the training data, does not generalize. We instead would have preferred to choose H3 in this scenario, a different hypothesis that achieved the same training loss, but better test performance. This is the problem of generalization. The good news is that our toy example suggests a better approach. Instead of just learning one way of solving the problem, we should learn to solve the problem in multiple ways. Then, by choosing the right hypothesis, we can tune for quick generalization. This can be like installing a tunable knob into our learned function. Now, let's tie this back into locomotion. Consider training a policy to walk on flat ground. The input is the proprioceptive state, and the output is the joint position targets. We will train this using reinforcement learning. Typically, in reinforcement learning, we train policies with multiple random seeds. This might incur some diversity. Shown here are 3 policies trained with different random seeds. However, we found that even when we train with different random seeds, the performance of behaviors does not vary much in new environments. There's implicit regularization towards a particular behavior. Then, when we encounter an out of distribution environment like rough terrain, we cannot do what we did before. We cannot choose a different hypothesis that performs better without modifying the environment and retraining the policy. To address this, we propose MOB, which introduces a style reward function conditioned on a set of behavior parameters. These parameters include gait attributes like contact timings, swing foot motion, and body posture. The style reward is designed using human knowledge about what parameters of gait can be useful to vary. We hope that this will result in a diverse, structured space of gaits. So let's see if it actually happens. You can observe the different behaviors produced by our single policy. The choice of behavior is determined by the behavior parameters, which are input to the policy. And the behavior parameters can be thought of as knobs. These knobs can be tuned at test time, potentially by a human user or a high-level policy. Let's see some real-world examples. Consider the robot walking on sand. When we shove the robot hard, it cannot resist quickly due to a narrow stance. So what do? Typically, we might retrain our policy with more shoves. But with MOB, we could just try tuning the knobs first. Let's widen the robot stance. It becomes much more robust to shoves. Later, the same robot encounters a set of stairs. What to do now? It was only trained on flat ground. The previous gait that generalized well to sandy shoves fails. Again, instead of retraining the policy, we could try tuning its behavior inputs. Let's tune the knobs to obtain a higher foot swing and slower stepping frequency. Now the robot can overcome the step. However, this gait that worked on stairs may fail when running on a slippery terrain. Let's tune our knobs again to increase the gait frequency and narrow the stance. Now the sprint is successful. Thus, when we take MOB outdoors, a human pilot can take a few attempts in the new environment to find a successful behavior in the parameter space. This idea holds promise for piloting the robot in situations that are hard to simulate, like thick bushes and complex terrain. Until now, we have shown that MOB can learn diverse behaviors for a single task. Now, the question is, can we transition from skill 1 to skill 2? The answer is yes. We show that MOB learns to compose multiple behaviors in sequence. By the way, this is a natural consequence of learning continuously parameterized behaviors in a single policy. We don't need to do anything special during training. This even serves to compose motions with precise timings and high speeds. Here, the robot's foot contact timings are precisely choreographed to music. Sorry, there's no audio on this one. So, what are our takeaways? First, MOB provides a procedure for learning a structured space of locomotion behaviors for each locomotion task. The diverse behaviors learned by MOB impact performance in unseen environments, sometimes improving it. This is further validated in our paper by a set of simulation studies. And finally, we train the many gaits in a single policy. Previous works have reported this to be challenging. It enables online composition of behaviors. But no CoRL presentation would be complete without acknowledging our dirty laundry. Of course, a human pilot was required to guide all of the adaptations shown in our videos. Future work could select behavior autonomously using imitation or self-supervised methods. Second, a human designer needs to specify the behavior space. MOB is of benefit specifically in settings where this is easier than designing and tuning improved environment models that represent the real world better. Finally, there is a limit on how far we can adapt using multiplicity alone. We can only choose from the space of policies that perform well in the training environment. These tuned gaits could be combined with continued fine-tuning on real-world data for increased performance. If these sound like interesting challenges, the good news is that you can help us overcome them. Our code is open source, and users have already reported success running it. This concludes my presentation. Thank you for your time.
Very cool, very cool. Before we get to the questions, I have to say I'm still amazed that you let your robot roll around in the sand That is just nuts. How many robots broke that way?
We fixed it a couple times. but
Okay,
they've survived.
just twice.
Yeah.
Yeah, go ahead, Carol.
Do you have an intuition? How does it compare to unsupervised methods where you would use a mutual information objective to find all the skill space as opposed to setting it manually?
Yeah, so that's a good question. And so we didn't do a formal comparison, but I guess based on what I know of those methods, it seems like it's kind of harder to obtain the behaviors that we might see here, where, for example, the robot swings its feet really high. Actually, we need to provide like a strong sort of incentive through reward for it to do that. And generally, the unstructured methods might result in like a lot of gaits that are feasible but not useful, like hopping on 3 legs, stuff like that. So in my opinion, it's important to provide some structure to that space, or at least it helped as a first pass. I am interested in trying out unsupervised methods in the future, though.
Cool, thank you.
So they experienced change in the behavior target within each episode. So in that sense, they did observe change between, but it was pretty rare, just like once per episode. Episodes are pretty long, and we didn't find, that we needed to make it like extremely frequent.
Yeah, I have a question. So, are there anything you did specifically for sim2real? You know, there are the lines of RMA like work, they use the appropriate safety information to do the online adaptation. And what did you do here in your case?
Yeah, so it's a good question. So we did, we do have a state estimator within our policy. It's just estimating the body velocity and it's learned. But we don't have any like RMA style implicit adaptation.
Good. Maybe the follow-up question is, can you remove that state estimator?
Yeah, so I didn't find that it had a big impact on the performance. So the policy does actually observe the entire state history. So it could sort of infer some state estimate, but mostly that estimate was being used for like analysis purposes. But I didn't formally ablate it, so I didn't notice a big impact. Yeah.
Thank you.
We've got a question in the back.
Thanks a lot, Gabe. It's definitely amazing. So I'm not sure if I missed it or not. So I'm wondering whether you have some evaluation metric to determine the discriminability between these behaviors, or it's more like eyeball or like observed behavior difference.
Yeah, so I guess there's no metric of diversity. Rather, it's sort of a space of behaviors that's designed by the human. So it's not a set of complete reference trajectories, but it is like a target that's grounded in some property of the robot. For example, targeting different body heights as one parameter of the behavior vector.
Yeah, great. Thank you very much.
Thank you very much, Gabe. That was very cool.
Thank you.
We're now going to hear about SE2 equivariant pushing dynamic models for tabletop object manipulations. No, that's not what we're going to hear about. That's right. We're going to hear about deep whole body control. Okay, I guess SE2 pushing, are you here? Are you in the room? Nope. All right. Well, here, maybe later. Maybe they'll appear. Zhipeng? No, that's all right. That's okay. We can switch the order. Go ahead.
Thank you for the introduction. And hello, everyone. I'll be presenting our work, SE2 equivariant pushing dynamics models for tabletop object manipulation. I'm Seung-Young Kim, and this is joint work with Byung-Do Lim, Yong-Hyun Lee, and Frank Park. Although we may not realize it, we use pushing manipulation in our everyday lives all the time, as this video of a human grasping object shows. Pushing manipulation is also an important skill for a robot, especially for scenarios like the following, in which the robot must extract and grasp an object that is surrounded by other objects. The classical model-based methods of solution would be to identify and locate the objects and use our knowledge of physics or mechanics to push the objects so that they can be manipulated. The problem with this approach is that the shape and mass inertial properties of the object, as well as friction coefficients, may not be known in advance. And in some cases, real-time motion planning may be difficult due to the heavy computation of physics-based models. To address these shortcomings of classical model-based methods, several data-driven methods have been recently proposed. These methods take as input a visual scene ST involving multiple objects, together with a user-provided robot pushing action AT. The output is then the next scene ST+1 of the objects after they have been pushed by the robot. Recent methods differ in the choice of visual input and deep neural network architecture. Compared to classical model-based methods, all these methods have the advantage of fast inference and do not require prior knowledge of the object and the environment. However, after we carefully compared the performance of these and other data-driven methods, we found that their generalization performance to be less than satisfying, and they require large amounts of training data. One way to reduce the amount of the training data is to use a network that is equivariant. We now explain what this concept means. Consider the following scene in which a single object on a table is pushed as shown. If the same object is now displaced to another location on the table and the same relative pushing action is applied, then the resulting displacement of the object should just be a displaced version of the original object motion. It should not be necessary to provide this type of redundant training data into the network. A network that possesses this property is said to be equivariant with respect to translations and rotations on the plane. Or more technically, equivariant with respect to special Euclidean group SE2 of planar rigid body motion. The main contribution of our work is a data-driven model for pushing dynamics that is SE2 equivariant. We now describe our SE2 equivariant network architecture. Here is a scene with a table and tabletop object. We first assume that the table surface is flat and orthogonal to the gravity direction and has uniform friction over the table. And for training phase, assume an object placed on a tabletop, and we know the information of the objects, including each object pose Ti and shape parameter Qi in large Q. Also, we consider a following discrete time pushing dynamics model F to predict the motion of the object 1. The model inputs the target object T1 and Q1, surrounding objects from T to Q2, from T and Qn, and pushing action AT. Then it outputs the displaced pose of the object 1, T1 over T+1. Using the same model F, we can also predict the displacement of the other objects as follows. Assume that the object and the pushing action is transformed by the same SE2 transformation C, then these variables look like this. Then the model is desired that each output should be also transformed by the same SE2 transformation C. In this term, we can define that pushing dynamics model F is SE2 equivariant if the following equations hold for all SE2 transformation C. In the test or inference phase, based on this definition, we first recognize the object poses Ti and shape parameters Qi from visual observation. The learned pushing dynamics model F then takes the shape and pose information of each scene and each object together with the pushing action and output the object displacement. The detailed architecture is as shown. Briefly, let object I with the green color be the object of interest. We first project the SE3 frame TI to our SE2 frame CI, which is restricted to lie on the tabletop. We note that the objects can be tilted in this formulation. And all objects together with the pushing action are then transformed by CI inverse. These values are then passed through several MLP layers, producing the output transformation delta TI. Finally, the next pose is calculated by multiplying the original pose TI by delta TI. This alpha value is SC2 equivalent. For evaluating the proposed dynamics model, we build a pushing manipulation data set in simulation. We use cylinder and cube-shaped objects and of various size as shown in right, and each scene contains up to 4 objects. Examining our results, we see that our method outperforms other methods for the unseen test data set. Although our method requires additional intermediate computations, it shows the best generalization performance using less training data. Shown here are qualitative results of predicting object motions after a pushing action is applied. Our model successfully predicts even complex interactive behaviors of the objects in the test dataset. We also confirm that the proposed model can be used for various downstream pushing manipulation tasks, including moving tasks that moves the objects to their desired poses, and singulation tasks that separates the objects by more than a certain distance tau. Moreover, our model can be directly used for assisting grasping tasks since our methods also estimate 3D shapes of the objects. We can generate candidate grasp poses for the recognized 3D target object as shown in the figure. Then, by checking collisions of the predefined grasp poses with the environment and the other recognized objects, we can define an appropriate reward function which has value 1 if at least one valid grasp pose exists and 0 otherwise. We execute action sequences that maximize the grasp reward function. Notably, without using any ad hoc objective functions, the robot realizes how to reconfigure the object so that feasible grasp poses for the target object can be found. The robot pushes the surrounding objects as the left and flat and large object to the edge of the table as the right. So here is a dirty rendered list. First, currently, it is not trivial to apply it directly to more complex and non-convex shapes. Especially defining shape parameter is not a trivial problem. Second, there could be some situations where the SE2 equivalence does not apply. In this case, our approach can be detrimental. Finally, different mass distributions will lead to different motions, especially when the objects interact with each other. In this case, the dynamics prediction task using only vision data becomes challenging. So finally, here is a summary. In summary, we have proposed a SE2 equivalent pushing dynamics model, and we confirm that our method significantly outperforms the existing visual pushing dynamics models. And finally, we have verified that our method can be used for various pushing manipulation tasks, especially for assisting the grasping tasks. So there are many more interesting topics discussed in our paper, and we invite you to take a closer look. Thank you for listening.
Thank you very much. We have a question from Jitendra.
There can be, I accept the argument that there's SE2 equivariance with respect to the object's motion, but you don't have that with respect to the manipulator, because for the manipulator, all points on the table are not equivalent, because if you think in the joint angle space, I mean, the force that, for example, if my arm is really outstretched, then it may be more difficult to apply certain kinds of forces than when the object is closer to me and I'm in a different point in joint angle space.
Thank you for question. We assume that the object-based force is the objects and the table is. I'm assume that the object and the table is far from the base frame, so we didn't think about the SE2 equivalence of the robot's joint space. So
Okay.
Yeah.
If I could ask an immediate question, in computer vision, a standard way to build in invariance is by just doing data augmentation. So you could take your training set and just do data augmentation just get your training examples and just shift them around and augment your data set. And then after that, you don't have to do anything fancy.
In this presentation, we didn't report that how the data augmentation technique works for our framework comparing to equivalence model, but we found that our equivalent network framework shows higher performance, better than data augmentation. So yeah, we confirmed it.
Thank you very much. I'd love to take more questions, but I really don't think we have the time. Let's thank our speaker. And our last presentation for today, you might have seen this before, is Deep Whole Body Control, Learning a Unified Policy for Manipulation and Locomotion, and Deepak will be presenting it. Go ahead.
Okay, hi everyone. Welcome to the last talk of the day. So Zipeng and Shuchen could not make it to New Zealand because of their visa issues. So here I am presenting their work on whole body control. So before I start, let me ask you a question. Apart from dirty laundry list, what is the next most common thing you have seen at CoRL this year? You can think about it. But for me, wherever I go, I see legged robots. They are there on the stairs. They are there where the food is. They are there. They are sitting here, and they are there in every talk, almost every next talk. So a lot of progress has been made in legged robots, and they can walk outside. They can walk in forests. They can walk in water. So the question is, what's next? How do I use this robot to do anything more useful? So just locomotion is restrictive. It's restrictive in the sense that they can walk around, do inspection, but I cannot do any manipulation with that. So the next step here is to add an arm. Like have a robot with an arm on top, and legs increase your reach. Arm helps me manipulate in the real world. Good, okay. So where do I get this robot? So we went online, tried to look up the existing models, and turned out the price tag is so expensive. We cannot afford these robots, especially in academia, or can afford only one in our career. So, so here is a Spot from Boston Dynamics with ARM, cost over 100K. Other one is from ETH, from Animal Robot, not on sale, it's not commercial yet. Okay, so what we did, we thought, okay, let's buy the cheapest legged robot out there, the cheapest arm out there, and put them together in a custom setup. So here is our low-cost legged manipulator, and you can see the details here. It cost 6K, which is 2 orders of magnitude less than the comparative robots. Now, the interesting part is with this platform, here comes a new challenge. You have to now control both legs and arm together. So this problem in literature is called whole body control. Now, this is an area where lots of work has been done in the controls literature for the last 15 or so years. But this introduces new challenges. First obvious challenge is that I have significantly increased the dimensionality of my robot. It's no longer just 4 legs, 3 motors each. We have a full arm on top, gripper, and all this. But the bigger problem is this introduces an obvious local minima in the problem. If your legged robot, for legs want the top to be stable. Like for them, it's the best when the arm does not move. For arm, base should be stable. It's best when the legs don't move. So they compete against each other. And there are a lot of approaches in the literature which are based on optimization. And if you open their method section, it looks like this. So there are lots and lots of modules, one module for arm and then one module for legs. And then you have to somehow engineer a new optimization to put them together afterwards. And this creates, this requires a lot of effort and may not always get optimal behaviors for you. So the question is, in the spirit of learning for robots, which this conference is about, our question here is, can we design a single policy? Can we learn a single policy to control the whole body of this robot? So before I go into the results or the approach, how do we do this? Let me show you some examples here. What do I mean by that? So in all these examples, what we'll show, human will only command the end of the arm, and the whole body has to account for this at a very high frequency. So if you notice this robot here, the human is commanding where the arm should go, and you can notice the legs can bend automatically. The body rolls to the sideways as you move arm to the sideways. So arm can reach much farther than it could reach otherwise. So here, human is controlling the arm end effector. So it's the shakiness you see is because of two reasons. Arm is very low cost, and humans are bad at this kind of thing. So what we are showing here, so in this example, arm is moving while the legs are walking. So it is stable in those situations as well. So here we tried to test the limits of human ability to control the robot with end effector. So here you pick up something, try to put in a trash, and the robot can walk and it can do the whole body control. But again, human is not very precise and arm is not very, so we are showing dirty laundry in the talk itself. In the spirit of science. So it can put it, it takes time for human to align the joystick. You're welcome to play with it in the poster session yourself. We'll have live demo here. We got a robot all the way from CMU across the world. And here it is wiping whiteboard, etc. Now, if you don't have human, you can also track using vision. This is a demo. Here, there is no human involved. You just track the AR tag from vision, and you can see the arm and legs being controlled together. So how do we do this? How do we approach this problem? Now, legged robots are everywhere, and the approach that you find, which is common across most methods, contains this two-step magic process. First, train a policy in simulation from some privileged data, like it can contain anything, like whatever it is available. In step two, distill this policy into something via supervised learning that from the information that is coming from onboard sensing, so that you can deploy it. To give an example, so one in this, like for instance, in this case, in phase one, you can train a policy with some privileged information like mass, friction, height, etc., and you learn this policy. In the phase two, you distill this policy into a supervised process from history of the robot. So this example is of our previous paper called RMA, but other approaches can also fall into this category. Now, what happens if we just apply this approach to whole body control? So we just take the same method and we apply here on arm and legs. It does not quite work. And when you put this in the real world, sometimes legs work, but notice here, there is slight slope. You cannot see in the image very well, but here the robot is trying to go forward and the arm is stretched out and it is not able to move forward because of the weight on top of it. And there are many more failure examples like this. So it does not work. So what is the issue in this approach? So let's take a step back and look at this figure again. What we are saying here, in phase one, we are compressing via RL. In phase two, we are distilling via supervised learning. And we are making an inherent assumption over here. And the assumption is that compression implies predictability. There is no reason, if you can compress something very well, you can also predict it very well, right? So this supports this issue. And as the dimensionality of the platform increases, there are more and more elements in the basis function. So it becomes very difficult to predict it. So to fix this, we perform a very simple trick. And the idea is, why not combine phase one and phase two together and learn to compress it while simultaneously making sure that your compressed vector is also close to the one coming from the history or any other data. So you train the phase one together with phase two, and phase one is trained to perform RL, and while simultaneously it is also trying to make sure that latent is close to the one coming from the history of the robot. So we call this approach regularized online adaptation, ROA. In addition to this, to account for the arm and legs, we also perform this something called advantage mixing. And the idea here is that you want to start with the reward function, which in the beginning tries to help arm and legs separately. But as the training goes on, like this beta goes from 0 to 1, and as training goes on, the objective for arm and legs becomes shared. So if you say arm should go farther, the only way for arm to go farther is to walk over there and then extend the arm. Like if I take my arm to that corner or something. So this is the method. And then we just deploy this policy in the real world as usual from history of the proprioception on the robot. And this is what this leads to all these results. And here are some, again, few more examples of the same robot doing different tasks with this whole body control. So let us see some results. So here I'm showing just 3 methods for now. In paper, there are more details. On top is our method. And you can see there are 2 metrics. The left one is arm workspace. So this whole body control increases the effective workspace of the arm itself because the body can bend to increase your reach. So imagine yourself trying to pick up some apple or something from the table. You can extend your reach by spreading yourself and spreading your legs. The bottom one, separate, is like modular approach. The last one is also a shared policy, but the reward is separate for arm and legs. And you can see our method performs best in both the metrics. And this is again updating advantage mixing. And you can see here the blue curve, the advantage mixing helps you obtain lower error in both the scenarios and perform, and is essential for the performance in this setting. So we also compare to MPC plus IK based methods in the paper. In the interest of time, I'll just skip them, and it outperforms them in both easy scenarios as well as hard scenarios. So let us see some dirty laundry. Now, here, dirty laundry is primarily coming from the fact that the hardware is very low cost. So if you see on the left, the motors heat up after 30 minutes, and you may have to push the robot to walk forward because its motor doesn't have enough power. So the more you run the robot, the behavior changes. And on the right, since we are doing position control, it's not very good for fine-grained tasks in the scenario. So now, since we got the robot all the way across the world, so we thought we'd just show you a demo as well in the live. So here, the end effector is being controlled. You can see how the legs are bending forward as you move the arm to left and right. You can see that these are not the authors of the paper. These are not well practiced to how to use it. But if you take arm to the left, to the right, it tilts to the right, tilts to the left. And if you take it up, if you take it up all the way, you can extend the leg and effectively increase the reach of the arm. But I can take questions. So this is, thank you. This is the last slide.
Thank you very much. You've got a question up there.
Hi, great presentation. I really liked it. My question was that some tasks require careful and precise movement of the arm, such as like clicking a button or putting the trash into the garbage can. But other tasks probably require, they're more extensive on like the legs. How does the advantage mixing kind of account for this? And like, what would you do to kind of improve precision of the tasks that you can do?
Yeah, so this is a very good question. And one thing I did not say in the talk, this whole training currently is agnostic to the end task. So think of this controller, like let's say you buy an arm from Franca Amica Panda. It already comes with a controller inside it. For any task, this controller works. So this controller is designed for any task in the end. So now we are yet to design a mid-level policy here that can do position control to perform tasks. So where we are using human in this work. But here, advantage mixing allows us to make sure that for any configuration of arm or the legs, this can reach it if it's possible physically. So for instance, if you say arm should go towards there, the legs can make the robot walk and then take the arm to that corner. So you don't have to worry about any low-level control like you do in Franca arm. Like it's a replacement for that, for this legged arm system.
Go ahead.
So you discussed about how compressing the Z space is not enough and we need to add this predictability term. I'm wondering if we directly predict the actions and not the Z, would that fix that problem?
So So the thing is, when you are trying to directly build the actions, you are trying to solve two problems at once in the beginning. Like you are trying to solve the estimation problem as well as solve the control problem. And the control problem here is very hard. So by having the Z vector, we first like separate these two problems into two parts, estimation and control. Then regressing the Z vector, the advantages gives us, like I showed in the dirty laundry, the robot heats up as it walks. So when it heats up, the CPU gets slow and your system has to be asynchronous at that point. Like you cannot hope that your history is being processed at the exact same rate at all times as you're walking. And this separation of latent allows us to take advantage of that. So it's completely asynchronous. So history can come at any time. You can use the latest latent and then work from that.
There's another question from online. The question is, what's the next step for quadrupeds? So is it training a high level policy, add a second arm, or something else?
So this is what the motivation of the talk was. So I hope this is the next step of the quadrupeds, or beginning of the next step, that where you have an arm and then you can put these platforms inside your homes. So this is a very small robot and very safe. You can see as you saw it here. So you feel safe around it. But all the other robots which have arm on top are this big, and it's scary. Like you can see a V1 robot over there. I feel scared around it. So the next step I hope here is that you take such robots, such platform, and put in homes and do all sorts of mobile manipulation. Like go up the stairs, take your beer and take up the stairs, not bring the beer on the same floor to the same person. And you can do all sorts of things, but hopefully this is where it goes.
Thank you so much, Deepak. I think this session is over. This session is over. I'd like to tell you that now we have an online poster session. As Karen said, a lot of the presenters in the online poster session are people that would have loved to be here but cannot be here. So please make the effort and go to the online poster session and chat with them. Thank you very much.
You can't change your destiny. God is